problems with the satellite images that we use to analyze data. So let's give him a round of applause and welcome Nikita on the stage. Thanks for having me. I would start with a small question. What the most popular application of machine learning do you know? Someone will say that it's a speech generation. Someone will say that it's a images classification. Maybe it's a data visualization. And there are a lot of useful applications of machine learning. And you will be absolutely right. But today I'm going to speak about less mainstream application of machine learning for satellite data. To detect fields, how to benefit from this, what problems we face and how we solved them. Okay, I graduated from Moscow State University. I have a master's degree in physics, but now I'm working as a deep learning engineer at one soil company. Our startup is located on the junction of agriculture and machine learning. And our main goal is to delineate fields borders and to detect crops. It's our main direction of developing and starting point to benefit for different agriculture needs. We have a platform where farmers from the whole world can use our satellite data to move towards precision farming. Precision farming is a new and modern notion in agriculture where you deal not with the field as a whole, but with entities that are smaller. You can think only within a particular field, and to achieve that, you need to know field's borders before. For example, here on the left, you can see one of our predicted fields. And farmers from the whole world can use our platform to watch in dynamic how fields that have been sown are developing. For example, on the right, you can see in dynamic how it's changing one particular field during the year. And green color represents how dense and healthy plants that are growing in that field are. Okay. Let's speak something about our data and where do we get them. Sentinel-2 is a mission of Copernicus program from European Space Agency. They have several satellites that provide us with multispectral data with high revisiting rate, 5 days, and huge spatial coverage almost all around the world. This multispectral data has different resolution for different channels, from 10 up to 60 meters. It means that each pixel on your image has at least 10 meters of length surface inside of it. It's a little bit higher than we usually see on, for example, Google Maps, but it has a free and open data policy and everyone can use this data. Here you can see different examples of our multispectral data that we use. For example, on the left you see true color. On the center is frequently used in agriculture vegetational index that show us how healthy crops that are growing in the fields are. The greener color is the healthy crops are. And you can combine different channels to have a lot of other useful combinations. For example, you can construct, on the right you can see moisture index from our data. Okay, let's speak more precisely about our task. We take data from Copernicus program, then we put them into some mathematical model, and as a result, we get mask where each pixel is marked with the number of field it belongs to. In computer vision, it's commonly known as instant segmentation task, and it's a little bit harder than semantic segmentation task, where you want to get binary mask where each pixel represents is it a field or not. Here you want to tell what field it is, if it is, and particular kind of model doesn't matter here. Keep in your mind that it's some deep neural network. Okay. Our input data are composed from multi-channel images. Here it's n channels for each image, and then we take several images of one particular region for several dates, and then we stack them together. And totally here we take t different dates, and each image has n channels, and totally we get n times t channels, one image with a lot of channels, and we get different dates to detect fields borders more accurately. Few words about preprocessing. What kind of preprocessing do we need? First of all, you can see that satellite data have a lot of clouds. They can be covered by clouds almost the most part of the year. Also, in some countries, fields can be covered by snow during 6 months of the year. And for that purposes, we build validity masks that show us where clouds and snow are. Also, there are other different masks that can show us where is the water on the image, for example, water mask, and then we union all that masks to get total validity mask that show us all visual obstacles on the image. For example, here on the top you can see cloud mask, then snow mask, and then combination of them. And we can use it to train our model and in our platform to not show our users clouds on their fields and snow, for example. Okay, are there any problems with our data? There is one extra problem that I wanted to explain, but to understand this problem we should dive a little bit deeper in our satellite data. Typical satellite image is comprised of two things. It's an ordinary multi-channel image, and it's a georeference. Georeference means that each pixel on the image has its own underlying georeference, has its own underlying coordinate. It's bound to the Earth's coordinate. And in general, our image is bound to some particular place. When we train our model, the most logical solution is to take as many dates as we have, because of some particular place, of course. Because at some dates, fields cannot be seen under clouds, under snow, and so on. But when you stack more dates, the probability to see field borders clearly increases. Well, it's the most logical solution. In practice, it works not as good as we would expect. Because when we get data from Copernicus, they have been already shifted. They underlying georeferences are shifted one relative to another. It can be seen as each image of some particular region, different dates, slides relative to other images from date to date. Here is one more nice visualization of this. It's a side view, and you can see that images, we bound them to Earth's coordinates, and you can see that they slide along space and during the time. It can be a little bit better seen if you take a look at red point. It represents some real objects, for example, it can be some building, and its underlying coordinates slides from date to date. Okay, here you can see how it looks in reality. Some field, and you can see that it jumps from time to time, from left to right, to down. Maybe guys on the back seats can say that these sheets are really small, and yes, but keep in your mind that each pixel on your image